Welcome, everybody, to the 59th episode of High Sky Monthly. Hopefully, everybody had a great weekend. We're so excited to have with us today Dr. Jack Brouwer. First, I'll just do some announcements, and then we will hear from our distinguished speaker today. As you know, this is High Sky Monthly. I'm Danielle McLean. I'm the founder and CEO of High Sky Society. And High Sky is a 501c3 nonprofit based in Houston, Texas, dedicated to advancing a community to advance clean hydrogen science. Our vision is expert scientists providing fun, sustainable science education to communities. Our objectives are to equip future professionals with hydrogen skills, build positive community relationships, provide industry-leading courses and webinars, and advocate for your hydrogen solutions. And as you know, we are very passionate about hydrogen aviation, as most of us come from aviation. And a special thanks to our sponsors, Piasecki Aircraft Corporation, the Vertical Flight Society, Therm & Co., and SoCal Gas. Make sure you go subscribe to our YouTube channel, and I will put the link in the chat. If you're not already subscribed, click that link and subscribe. It really helps us to grow our audience. You can always sponsor these webinars. So this webinar is recorded. And if you sponsor a webinar, they start at $1,200. It goes on our YouTube channel forever. And you also get a shout out in webinars like this. So consider sponsoring for $1,200. We are also in the middle of our Advanced Hydrogen Technologies and Design course. It started October 8th. It ends November 7th. You can still register. If you do register, you're able to download the past lectures. There are 4 parts to this course. It starts with the fundamentals of hydrogen and cryogenics. Part 2 is fixed wing aircraft, which we're in the middle of right now. Part 3 is eVTOL, hydrogen eVTOL design. And part 4 is hydrogen infrastructure. This course is amazing. It's taught by Matt Moran of Moran Innovations, also a NASA retiree, the VP of Engineering from Universal Hydrogen, Antonio Tripoli. The eVTOL design is Anubhav Datta, who many of you are familiar, does the H2 eVTOL design teaching. And then finally, Gail Labrie of WSP, he does the airport hydrogen course. So this is like the most extensive course to date. If you're looking to train your employees or you want to learn more about this, I highly encourage you to register. Like I said, you can access the past lectures. So even though if you've missed a few, you can still access them if you register. And then I will pass it over to Rishav. Rishav, are you with us? I don't know if Rishav is here yet. We've had some scheduling issues. That's okay. I can do this next part. It's my favorite part of the webinar where we are all going to turn on our camera and take a group photo. So go ahead and turn on your cameras and let's do a group photo. I probably need to stop screen sharing and change my view. Okay, there we go. It's always so good to see your faces. It makes it so much more realistic. Wait for a couple more to turn on their cameras. We'll do a couple. Okay, we're gonna do 1, 2, 3, say cheese. Let me save that and then we'll do another. Okay, 1, 2, 3, cheese. Let's do one more. All right, everybody say cheese.
I thought we should say
Awesome.
hydrogen.
I know. Okay, let's do one more and we'll say hydrogen. I wonder how that will look. Okay,
I don't know.
1, 1, 2, 3, hydrogen. I think I actually smiled more on the hydrogen one. That's great. Okay, cool. Oh, Rishav, you are here. Awesome. Okay, I will pass it to you.
Hey, hey all, sorry for the technical issue. Yeah, sometimes it happens to every one of us. So I'm just glad you're bearing with me. And welcome once again to the 59th episode of High Sky Monthly. Today, joining us is a very prominent person who's is in the hydrogen space, Dr. Jack Brouwer. He is an energy system dynamics expert with a focus on renewable energy systems, dynamic simulation and control, energy system thermodynamics design integration. Um, Jack is a very um, diverse person. His research interests also include electrochemical conversion devices systems, fuel cells, electrolyzers, batteries, hydrogen production, storage, and conversion systems. He is a professor and a Chancellor's Fellow in Mechanical Aerospace Engineering, Civil and Environmental Engineering, Chemical and Biomolecular Engineering at the University of California, Irvine. He's also the director of the Clean Energy Institute, UC Irvine. He is also involved with the California Hydrogen Hub. I'm not going to get into that right now. He serves as the associate director at the National Fuel Cell Research Center, and he's a professor at the University of California, Irvine. He's gonna be talking today on the innovations in hydrogen fuel cell technology, a path to sustainable aviation. Jack, great to see you again, and I'll pass it to you.
Thank you very much. I appreciate your invitation and the opportunity to speak to you all. I tried to share and couldn't yet. Now
Try
I
try
can.
now.
Yeah, now I can. No problem. Um, I've had a very long-standing interest in hydrogen use in aviation. Started doing research in the late 1990s. Yeah, late 1990s for use of hydrogen in aviation applications. My particular interests were associated with not using hydrogen in space because that was already very common, but because of its lightweight characteristics, I knew that it could possibly be used as a future zero emissions fuel for aerodynamic applications, terrestrial applications, not space applications. Um, Over the years, I've had many awesome students, awesome postdocs to work with, and colleagues at NASA and at Boeing, Airbus, and a few other places, Parker Hannifin, for example, that I worked with to um, evaluate and to conceptualize and then to thermodynamically and dynamically analyze the potential for hydrogen to be used in aircraft. And today I'm going to talk about work that's been primarily accomplished by two awesome students. One who, in the meantime, became a former student, Khalid El-Samri. Just this last week, he defended his dissertation. So Khalid is one of my awesome students that produced these results here. Sajjad Razay is my other graduate student that helped to produce the results I'll share today. I'm going to talk about the thermodynamic and dynamic performance characteristics of retrofit and new hydrogen aircraft designs. Now, hydrogen, because of its lightweight features, has been considered for flight for a very long time. As a matter of fact, you can see actual tests going back to the 1950s. And you can see from this Adler et al. Source here that there are many different examples of hydrogen used in flight. Most of those are combustion-based hydrogen, and you can see, especially when you get into the larger aircraft with larger design range, you can see a lot of red dots out here. Some of them have been using fuel cells and or hybrid configurations usually in this smaller design range of flight regime. And the other thing that the industry hasn't spent much time on yet are two emerging technologies, and they've been an example of the kinds of things we've been looking at lately. One of them is solid oxide fuel cells, and we know there are challenges implementing a ceramic fuel cell on flight, but we think it might have some very distinct advantages. Another is cryo-compressed storage, which is emerging as the most energy-dense way to carry hydrogen. So we've been looking at various aircraft and understanding their characteristics, looking at alternative powertrains for a retrofit type of design, as we are showing here, and sometimes for a purpose-built design. And so here you can see a couple of Cessna models that we've looked at. Here's an ATR model. We've looked at the 777 and also BWB and 737 aircraft. And we're looking at solid oxide fuel cell gas turbine systems, but also hydrogen combustion in gas turbines, but also proton exchange membrane fuel cells, depending upon the study that we are undertaking. And notice various design ranges. You notice that the historical limit was to have hydrogen primarily focus on the shorter range. But we believe, because of our analyses, that purpose-built aircraft can also go for these longer range applications. So what are some of the powertrains that we have conceptualized and analyzed? The first is, of course, the traditional turbofan, in which case we can simply substitute a hydrogen combustion system for the typical Jet A combustion system that exists today. And manufacturers have been advancing this hydrogen gas turbine combustion technology for many years. And so it's very possible to actually do this in the future with some combustor and maybe turbine modifications. Another technology that has been pretty widely evaluated is the proton exchange membrane fuel cell, in which case the liquid hydrogen that's on board is simply evaporated and placed directly into the anode compartment of the proton exchange membrane fuel cell. It has to have some air compressors to make sure we have sufficient air pressure and volume at altitude especially. It also needs to reject heat through this radiator system, which might be one of the biggest challenges for proton exchange membrane. And this is one of the reasons why many people are looking at high temperature proton exchange membrane. The most novel one that we are looking at this moment is this solid oxide fuel cell gas turbine system, which doesn't need separate cooling from the airflow that goes through this fuel cell, and also produces heat that is sufficient for running a turbo generator. Okay, so you can see that the heat that comes out of the solid oxide fuel cell is sufficient to run this turbine, which provides shaft power to the compressor, which provides pressurized air to the cathode of the SOFC, even at altitude. So this is a pretty interesting advantage. Two things. We can convert the solid oxide fuel cell heat into pressure for air delivered to the solid oxide fuel cell. We can also produce additional electricity from the high temperature, high pressure gas stream that goes through this turbine. And we also don't need then the big radiators for rejecting heat to the atmosphere. Okay, but all of these have their place, I think, in a hydrogen for aviation future. I already went over most of this. We see how this solid oxide fuel cell gas turbine system works, but here is an artist rendering of how one might look, where you see that we also have a battery energy storage system. Almost all of our fuel cell concepts for aviation include some battery energy storage because it can help a lot with the dynamics that are required for aviation. So the bulk of the system for this SOFC GT system is the solid oxide fuel cell stack, but then you can see various other components, the recuperator, oxidizer, generator, turbine, and compressor. So one of the retrofit analyses that we did was for a Citation XLS Plus. And because of the large volume that hydrogen takes, even when stored as a liquid or as a high pressure gas, almost always we lose some of the capacity for carrying passengers or the like. So for example, in the Jet A case of the Citation XLS, without any modifications whatsoever to that aircraft except to remove 2 seats and to place hydrogen storage in that space, and also hydrogen storage in the back of the aircraft, we've essentially just moved the kitchen from this location to the back here. And you see, we now have a passenger jet that takes 6 passengers instead of 8 or 9 passengers. Okay, so again, we have an analysis that suggests we have lower fuel rate and lower fuel weight, and also lower fuel amount that is required because of the higher efficiency, but we have larger fuel volume. Okay, so it's the volume that is the biggest challenge, not the weight when it comes to hydrogen. And people have known this, but what we are seeing is that with a reduced capacity for carrying passengers, we can certainly actually retrofit this Citation XLS Plus. Notice that the mass of the fuel is way less than the mass of Jet A. This is partially compensated for by a higher mass of the tank. Okay, but it's still lower maximum takeoff weight. In addition to analyzing the feasibility of retrofitting these aircraft, we also are doing life cycle, techno-economic, and emissions analysis. So this is looking at the life cycle assessment of a Jet A fuel on the top and a hydrogen fuel on the bottom. But essentially what we're looking at is everything from the production, the recovery and extraction of raw materials, et cetera, all the way to its aircraft operations and conversion, and looking at the emissions associated with that. And this is the bottom line for this particular assessment, where we see that the highest emissions are for the Jet A case, right? Over 6,000. We have lower emissions even if we use gray hydrogen, that is hydrogen that we produce from natural gas. We get even lower emissions for the combustion of green hydrogen, that is hydrogen made from renewable primary energy. And then finally, you can see even lower if we use this gray hydrogen in a solid oxide fuel cell or green hydrogen in a solid oxide fuel cell. It's order of magnitude 1/4 of the emissions of the Jet A case. And you can see here the gray and green hydrogen results for combustion. Okay, so even burning hydrogen made from natural gas in an aircraft saves almost 10% of well-to-wing CO2 emissions. Well-to-wing CO2 emissions, and 50% reduction if you use green hydrogen. And then if you use a solid oxide fuel cell, because of its higher efficiency, you have half the emissions with gray hydrogen and about, like I said before, 75% reduction, about 1/4 of the emissions. Well-to-wing. A second thing we do is techno-economic analyses, and you can see here that we have a lower fuel cost for the Jet A case, except for when you compare it to solid oxide fuel cell use of gray hydrogen, because gray hydrogen, also made from fossil fuels that are cheap, okay, can get us the lowest fuel cost. In any case, we have a 5% decrease and 17.87% increase in takeoff weight for the hydrogen combustion and solid oxide fuel cell aircraft, respectively. Again, this solid oxide fuel cell hybrid has a much higher weight itself compared to gas turbines. And secondly, has battery on board and the extra weight of the hydrogen storage tanks. That's what makes it a little bit heavier. But the fuel cost is reduced by 29.3% when replacing it with combustion and solid oxide fuel cell gas turbine hybrid systems powered by gray hydrogen. Okay, a second retrofit that we did was for a different flight. This was a flight that went from Dulles, okay, in Washington, D.C. area, all the way to St. Thomas, okay? And this is a Cessna Citation S550 S2. And again, we had to place some of the solid oxide fuel cell systems here, and it reduced the number of seats that were available in this Citation. But we were able to make the flight work and had a total takeoff mass that was below the maximum takeoff weight. And when we looked at these analyses, we found that we could get 13% below the maximum takeoff weight. Again, the key challenge is that the solid oxide fuel cell and battery systems take up a lot of volume. The volumetric energy density of Jet A and the power density of gas turbines is probably never going to be beaten by our alternative fuels. Our alternative fuels will take up more volume. Essentially, that's what we're dealing with. Okay, but if we design a purpose-built aircraft or have a retrofit that can go into a blended wing body, then we have extra volume, or at least more volume, for not placing the tanks where we would otherwise place passengers, but back into the wings. So you can see this here. We have hydrogen tanks that can go into the wings of this blended wing body. And again, we've looked at both 365 passenger blended wing bodies and tube and wing designs for 365 passengers like the 777, but also of the 737 retrofit that you can see. Yeah, which is 162 passengers, right? So this is the retrofit and purpose-built designs that we've looked at, number 5 and 6, 162 passengers for both the blended wing body and also the tube and wing aircraft. We also developed a physical model of the liquid hydrogen storage tanks on board, both for simply cryogenic hydrogen and cryocompressed hydrogen. And this is the storage technology that can have hydrogen stored at the highest density. You can see here we can go all the way to 87 kilograms per meter cubed, whereas liquid hydrogen is only about 71. And we developed physical models of these to simulate the heat transfer through the multi-layer insulation, that's what MLI is, and the vacuum and the aluminum walls that are a part of this type of storage technology, and all the physics associated with it, so that we can actually simulate not only the steady state capabilities, but the dynamic capabilities. What happens to these tanks as a result of applying them in aircraft if we have different types of insulation here, right? So a vacuum insulation or multi-layer insulation that is typically used in these liquid cryogenic storage. You can see is that we can reduce boil-off rates and we can change them from 5 grams per second to 3.8 grams per second if we use a lot of MLI, right? This multi-layer insulation. It's one of the best types of insulation that people are using in cryogenic systems today. One of the key things is that we think you can design tanks for storing the liquid hydrogen that I received a phone call here. I'm trying to make sure it isn't because there's a problem with this broadcast. Is everything working okay here?
Yeah, it's good.
Okay, great. Thank you. All right. So, okay, one of the key things is we think you can design the boil-off rate to essentially match your cruise fuel consumption rate so that you don't have to vent any hydrogen and that you don't also need to introduce any heating purposefully to your storage system to actually get the hydrogen out of the tank. Okay, so this is a very interesting part of the dynamics of storing hydrogen, cryogenic or cryocompressed, in these designs. Okay, we're showing this now for the dynamics of a blended wing body hydrogen tank as it goes through a flight over about 40,000 seconds. Okay, and what you can see here is that we have the liquid hydrogen that is depleting as we go down in as we use this hydrogen in the tank. But the gaseous hydrogen stays about the same. It goes up a little bit because you have more volume to store it over time. And then you can see here the gaseous temperature goes down, and so does the tank pressure. Okay, this gaseous temperature goes down because we haven't perfectly matched the regular boil-off rate to the actual extraction of the gas. And so we are lowering the pressure, lowering the gaseous temperature over time. But it's working out almost perfectly here, right? It has a temperature that ranges from 30 to 20 Kelvin. And this is a very nice temperature range for keeping this liquid hydrogen in the tank. Okay, and extracting as much of the gas as we can. Now, what happens in these various aircraft that we've considered? This is the 777-300ER, okay? This is the 365 passenger aircraft that we are comparing, the BWB 365 that uses hydrogen, and the tube and wing, but not retrofit, purpose-built tube and wing 365, essentially adding a little length of the tube to actually fit everything in there and still carry all 365 passengers, okay? What happens to these large aircraft designs is different from what happens to these smaller aircraft designs, the 737-800 compared to the BWB-162 and the tube and wing 162, as a function of propulsion and fuel storage technology. Okay, so what you see here is that the operating empty weight of the Jet A case is the lowest in all cases. Okay, no matter what, the empty takeoff weight is lower for Jet A. It has the highest gravimetric and volumetric energy density. On the other hand, you have to carry a lot of that fuel around. And so the total takeoff weight is actually higher than that for the hydrogen BWB. Partly because the BWB is more efficient in flight, but partly also because the hydrogen is so much lighter weight. We also have the lowest takeoff weight that's associated with the tube and wing, purpose-built 365 aircraft using hydrogen. Okay, so the payload and fuel weight of hydrogen aircraft goes down no matter what the design, BWB or tube and wing. On the other hand, if we're dealing with smaller aircraft, this is the lowest takeoff weight, okay, for the kerosene case. It goes up a little bit for the hydrogen BWB, and again, primarily this happens because we have much higher takeoff weight for the empty takeoff weight. And the same thing goes for the hydrogen in the tube and wing design. Again, it goes up primarily because the tank weight is greater for the hydrogen case. And again, even though we have fuel savings, it doesn't catch up to the original lightweight characteristics of the 737 with kerosene. But anyways, these are all in the range of operating these aircraft like we operate them today. Okay. Here you can also see then some of the hydrogen aircraft comparisons, okay, to kerosene in this larger class. We haven't yet tested anything in the 380 class, okay, or evaluated anything there, but this is in the 777 class here. And then you can see that in the, these all fall in the operating empty weight and megajoules per passenger range, okay, that are feasible for these future aircraft. Notice that we actually have a lot less megajoules of fuel required per passenger for these hydrogen aircraft. But we need that because hydrogen is less volumetrically dense. Okay. What about conventional emissions? Okay, like the nitrogen oxides, the carbon monoxide, hydrocarbons, and CO2 associated with these hydrogen aircraft. What you can see is that the kerosene 777 compared to the hydrogen BWB 365 and tube and wing BWB has much lower CO2, quite obviously, because we're burning or converting hydrogen in fuel cells. When we convert hydrogen in fuel cells, we have also very low NOx, okay, and zero CO2 and hydrocarbons, okay. And then if you look at the CO2 kilograms equivalent per passenger mile. And again, equivalent accounts for the effects and emissions or other things that could have a global warming potential. What you see is that in all cases, we have a huge reduction in global warming potential associated with all of the hydrogen cases compared to kerosene. And I guess this is one of the main motivations for doing this, right? It's to lower greenhouse gas emissions associated with aircraft. And you can see here, we're talking about something that's like a fifth to a fourth of the total emissions for the hydrogen BWB and tube and wing cases compared to the kerosene cases. Okay, so what are the general trends? Our operating empty weight is increasing due to the extra weight of the tanks and other features and the conversion technologies, right? The solid oxide fuel cell weighs a lot more than the gas turbine. But the fuel weight goes down quite a bit, okay? So the fuel weight is down 23% in the 365 case, down 28% in the 162 case. 61% lower fuel consumption, 52% lower fuel consumption compared to the tube and wing kerosene case of the 737. Lower maximum takeoff weight, okay, by 22% in the larger aircraft, but a little bit higher takeoff weight in the 737 case. NOx emissions are down tremendously for these hydrogen and fuel cell cases, and the CO2 equivalent emissions also down tremendously compared to the kerosene case. Okay, one last thing that I'll talk about, and then we'll take some questions, is associated with the fact that, hey, if we're going to be using hydrogen in aviation, we're going to have to deliver that hydrogen to aircraft at airports. And one of the airports that we've begun investigating is LAX. When I was at the High Sky event in Las Vegas just last month, I saw some results from a SoCalGas study that also looked at LAX. Ours is a little bit different than that, but what you can see here is that we were looking at the dynamics and thermodynamics. So in other words, what's the overall energy efficiency and energy demands associated with bringing hydrogen to LAX? And what are the dynamics of this? Because in all cases, we're starting with renewable primary energy to make the hydrogen. And we put it through electrolyzers to make the hydrogen. These are just 4 different scenarios, A, B, C, and D. So we're making it all with renewable primary energy and electrolysis. And we're either liquefying it and storing it right there, or we're making it offsite and trucking it in, or making it offsite and gas pipelining it in. Okay? These are kind of 2 of the main ways we expect hydrogen to be delivered. We're going to be delivering it that way in our California Regional Hydrogen Hub, for example. And then once you have it on site at the airport, you have 2 different ways that you can deliver it to the aircraft. You can also put hydrogen pipelines in the airport to serve each of the gates, okay? Or you could have trucks that drive to the aircraft at each of the gates. Okay, so those are the 4 scenarios we're looking at. Okay, we also looked at these 4 scenarios for 2 different demand cases. One for 2030 and another for 2050. And notice, we're not expecting hydrogen to meet all the demand of aircraft. Actually, it's only a fraction of the total demand. In 2030, we're expecting only about 5% of a flight transition to hydrogen. And in 2050, about 20% transition to hydrogen. This is consistent with what the literature is suggesting. Most people think that sustainable aviation fuels will be the main thing that we use to decarbonize aircraft. I think hydrogen is better than sustainable aviation fuels because you don't put the carbon back out into the atmosphere and have to have another means of taking it back out. It's also more energy efficient. It also has zero criteria pollutant emissions, which are super important. Okay, so I think hydrogen's better, but most people say it's not going to be that much of the total flight transition. That's what we're assuming in these cases. Okay. So what are we looking at? We're looking at the availability of solar and wind near LAX. And you can see here's where LAX is. And we do have solar potential that is very good in these regions around LAX. But if we made solar electricity in these regions around LAX, we either have to transmit the electricity to LAX and then make it on site, or we make it over here and transport it to LAX. Similarly with wind, LAX is right here, but you can see there are some very nice wind farm potentials out here. This is the map at 50 meters height. Very outstanding and excellent wind capacity offshore here. Okay, so these are the two main primary energy considerations we are making at LAX. And what you can see here is that if we do the techno-economic analysis, we're going to also account for all of the transmission, either of electricity or of the hydrogen, okay? And hydrogen either via truck or via pipeline, and paying for the pipeline to go from these places where you could have very good solar potential here in the desert, all the way down to LAX, and also from places where you have good wind resources to deliver that hydrogen or electricity to LAX. Okay, and of course the wind is very close. It's only 5 kilometers away. The solar is further away, 75 kilometers. By the way, pipelines like this and transmission lines like this are already being invested in by our utilities. SoCalGas, in their Angeles Link study, is looking at building pipelines like this to take hydrogen that's made in the desert and to deliver it to LA. All of our electric utilities are looking at putting additional transmission infrastructure from the desert and from places of high wind, like Tehachapi or further south in Palm Desert and the like. They're looking at these wind resources and solar resources and saying we got to use more of those and we got to deliver it to LA. So this is not something that is infeasible. We're studying it right now, investing in it right now. And it will be part of ARCHES, our California Regional Hydrogen Hub. Okay. Okay, so some final things. When you want to receive all the hydrogen from renewable primary energy, you have to consider the dynamics. Now, this is just showing the average annual dynamics for the total power that is generated. This is the black line that you see here, right? And this is a mix of sun and wind power. And it's, again, about an average of 2.5 gigawatts. And you can see here that the solar power, it's what you expect. It's only on in the middle of the day. That's this blue. But the wind power has this dynamic. And when you put those two together, plus the storage that we account for, right? Because the storage has to be charged and discharged at some times, okay? Then you can actually meet the power demand. And you can't get the techno-economics correct unless you account for these dynamics, right? How much do we need to store every day? How much do we need to store every month? And how much do we need to store for every season? Okay. These are the levelized cost of hydrogen numbers that we are getting from these analyses. And there's a couple of things to note here. What you can see here is that by far, the majority of the cost for making the hydrogen, both in 2030, when we have higher costs, again, this is because all of the technologies cost more, and in the case of 2050, when we have lower costs, the majority of the cost is associated with making the renewable electricity. For example, this is a cost of hydrogen associated with wind. That's the orange color. The cost of hydrogen associated with solar, that's this blue color, okay? In the end, the cost of the electrolyzer system, the compression, the battery storage systems that you have to couple to it, the cryo pumps and liquefaction, these all add to the cost, but much less to the cost than the cost of renewable electricity. So, and other researchers are finding this too. In the end, the cost of renewable hydrogen is primarily going to depend upon the cost of renewable electricity or renewable primary energy. Okay, and if those costs can keep coming down as we expect them to, then we're going to also have cheap hydrogen. Okay, look at these costs for 2030. Okay, a lot of people, get caught up in this idea that we have to get to $1 because DOE made a stretch goal when they established the hydrogen Earthshot. $1 for 1 kilogram within one decade. And I think this is a really cool and really nice goal. But that goal suggests less than $3, less than 3 cents per kilowatt hour for the primary electricity. And our estimates are that we're not even getting to that in 2050, okay? That's really, really cheap electricity. And if you account for the transmission and all the other stuff that you have to account for a highly renewable world, we're estimating something that's higher. But notice, even with these higher cost assumptions than the DOE target, we're getting something like $6 per kilogram of hydrogen in 2030. That's not quite competitive with Jet A at this moment, but look at where we're getting in 2050, $3. And again, this is for all-in costs. The liquefaction, the transmission and distribution, the storage of batteries and everything else that's associated with it. I am sure that the renewable energy future is not only going to be one that has these zero emissions, zero criteria pollutant and zero carbon emissions, but it also will be something that is cheaper than our current energy paradigm, which depends upon fossil. So I have a very optimistic view of the future. I think that with these technologies, I know that with these technologies, we're going to get down to these numbers. If you just look at the science associated with cost reduction over time, and we look at learning rates and everything else and apply it to historical technologies that have come down in price, like solar and wind and batteries, this is what's going to happen. We're going to have hydrogen available for aircraft, hydrogen available for making sustainable aviation fuels, and it's going to be cheaper than our current fossil paradigm. All right. We've done a lot of other work. I'm not going to talk about all of these here. We're grateful to our previous collaborations with NASA and Boeing, and especially recently with the Aircraft Systems Laboratory at UCI for the work that we've done here. And I'm happy to take your questions. Thank you.
Wow, thanks so much, Jack. Absolutely fantastic presentation and very incredible charts. That was one of the most thorough studies that I've seen to date. So yeah, kudos to your team. That was fantastic.
Thank you.
I'm just gonna, yeah, you bet. Those were really good charts. I could talk all day about those, but I'm gonna get to the questions.
Sure.
Okay, first we have Gaber. Gaber, do you want to unmute and ask your question?
Yeah, sure, that would be fine. I was just curious, earlier on you showed that the product of the solid oxide fuel cell is heat to drive a turbine.
Yeah.
Is that the primary product? There's also electricity being produced. I mean, what is the ratio of utility between those two?
Very nice question. It primarily produces electricity, and efficiencies for solid oxide systems in commercial applications already show about 60% fuel to electricity conversion efficiency. And so 40% or so comes out in the form of heat. You can't use all of that heat, of course, but if it's high temperature enough, it has good utility in the turbine, order of magnitude something like 25, 30%, okay, efficiency for the gas turbine to make electricity. But notice it then also makes high pressure gas. And this is the biggest benefit for aircraft applications for solid oxide fuel cell gas turbine technology, I think. It's that it not only has high efficiency, but it can operate at pressure when you're at altitude up on the waste heat from the fuel cell. And the PEM fuel cell, while it's more energy dense, more power dense than this fuel cell gas turbine system at high temperatures, it has to carry along a bit of extra weight for heat rejection and doesn't have this pressurized operation. You have to put electricity into a compressor if you want pressurized air at altitude. So I think that there's some really interesting benefits, especially at altitude.
Okay, great answer. Thank you.
Thank you.
Next up, we have Tiffany. Tiffany, would you like to unmute and ask your question?
I think it was kind of overcome by events. It looked like when you were retrofitting the citation that you were just kind of leaving the engines there. And so I was wondering if you could, put storage there, which it looks like you did on the tube and wing.
Yes. We did leave the engines there, of course, for the hydrogen combustion cases because we assumed they would be retrofitted with hydrogen combustion technologies. In all of the cases for the electric propulsion, we assumed that there were also these engines that were operated off of motors, which are the N30 motors. I think it's N30. I can't remember the number right now, that NASA has been developing that are cryogenically cooled and have lightweight electric propulsion that you spin through also a turbofan type of arrangement. Okay,
so you left them there and you were kind of just using them as almost APUs?
No. We don't use them as APUs. We use them for the propulsion itself, right? So the engines are used for propulsion themselves, but we assumed that they were retrofitted with the electric motors that drive the fans.
Okay, all right.
Yes.
All right,
Yeah,
thank you.
and it's similar in the design, the purpose-built aircraft, but they were a distributed propulsion design that we used in the BWB case, for example. Okay. Right? I don't know if you saw the engines that went across the top of the body. Yeah.
Yeah, no idea. Are we going to get the slides though? Because those were very interesting. I'd love to look at those.
Yeah, I'll share those with you, but I'll go to the presentation here a second. Excuse me. I'll share my screen again just to show you a couple of the cases, just to look at the design a little bit.
Yeah, see on the tube and wing, it looks like you have the hydrogen tanks where the engines.
Okay,
were on the
here's where the hydrogen tank is. Okay, here's where we have the mounted engines. They're mounted on the wing, just like the traditional case. I'm going to get my pointer so you can see it a little bit easier. So in the tube and wing, essentially, we're just putting hydrogen in the back of the aircraft here. Okay. And then we're putting the engines on the wing here. So it's more like a traditional design. In the blended wing body, you can see here we have 10 center body mounted engines that are in at the back of the aircraft like this.
Okay.
Okay.
All right, thank you.
Yes, you're welcome.
Great. Next up, we have Blake. Blake, would you like to unmute and ask your question?
Yeah, sure. So I understand the analysis that you were showing. The system would be heavier, although the overall fuel would be less, so the yes. takeoff weight would be less.
It's not necessarily for the smaller aircraft. The smaller aircraft, we still have a little bit higher takeoff weight.
Okay, so my question is then, do you run into constraints with the landing weight, right? Because typically, especially the larger aircraft, they can't land at their gross takeoff weight.
Yeah, that's very interesting. No, we don't run into those problems, but that's a very nice question. As a matter of fact, I think hydrogen is going to have a very distinct advantage with regard to this, because it has a very small difference between takeoff weight and landing weight. Okay, so the key idea here, okay, when we operate with Jet A, right, if you take off and have an emergency landing, you have to dump all the fuel. I don't even think we need to do that in the hydrogen case. And again, it would depend. Okay, you have to design your aircraft. You can't design it for heavier than maximum takeoff weight and also landing weight. So you're right. But I think hydrogen may have an advantage in the end in that, because the fuel is so light, there's not very big of a difference between landing and takeoff.
Okay, great. I did have one quick follow-up question. I'm just wondering, in terms of the temperature of the solid oxide system. So I know historically they tend to have fewer thermal cycles that they can go to because of the higher temperature, and it's usually a significant amount of time to warm the membrane up. Did you guys look into that at all with this technology? Is there something to address that so that, say, it could still work within the timetables that airliners usually use, or yeah, passenger aircraft usually use?
Yes, a very nice question again. We haven't looked at this for the specific case of aircraft. On the other hand, we have investigated this many, many times for using solid oxide cells to complement solar power. And what we have found in almost every one of our designs, including experimental analyses and modeling, is that overnight, the solid oxide fuel cell with appropriate insulation can start almost instantly. Okay? It can keep its heat to a sufficient temperature that you can start it again in the morning. Okay, so there's order of magnitude, half a day that you could turn it off and then start it right away. And this is what we think is going to be done for aircraft. They don't even have to be off that long. I mean, most aircraft, will be off for maybe 8 hours at night or something like that. And we know that with proper insulation, the solid oxide fuel cell will still be warm enough to basically start right away. Again, okay, let me just confirm something else you said. You said it takes a long time to get the membrane hot. Okay, that's for the first startup. It takes like 24 hours. Okay, if you start room temperature, it takes 24 hours to get it up to temperature. Okay, but then if you turn it off and don't do anything, it'll stay at temperature, I don't know, for like a week. But it goes down like this, but if you start it the next day, okay, it can go back up again pretty quickly.
Okay, and then the other part of that question that I had is, like, do you see that even with that type of a use that you would get the same number, or you'd get enough cycles out of it that it would be comparable in the long-term cost as like we currently see with gas turbines?
Yeah, very good question. Also, thermal cycling of solid oxide fuel cells is the most stressful thing that they undergo in operation today. But it's really the full thermal cycles that are a problem. So if you operate it at temperatures that are oscillating between, let's say, 650 and 850 C, okay, and maybe even every day going up and down like that. That's not as stressful as even one time, okay, going all the way down to room temperature and then bringing it all the way back up. So those full thermal cycles, we know that the systems can take around 10 of those or so today. And then a whole bunch of these cycles. Again, this is a more detailed study than we have been able to accomplish at this time, but I'm optimistic that we can overcome that with time. There are some other challenges too with solid oxide, in particular the ceramic materials themselves, which are not as robust to impact loads. Okay, impact loads. So when we're landing, we have to have some means of like not having a big impact to those cells, which is something also we haven't studied, but we know it's a challenge.
Okay, yeah, thank you. I appreciate it.
Yeah, thank you.
Okay, next we have Will, and then Santh will get to you, and then we'll probably end. I think I mentioned to you all this webinar will be a little bit shorter. Jack's got a class. So Will, if you want to unmute and ask your question.
Okay, can you hear me?
Yep.
Hi, Danielle. Hi, Jack.
Hey, Will.
Yeah, so I'm looking at all the work you guys have done, and that's a lot of work. And you've gone pretty far. Yeah, you've gone pretty far down the road for it. And so, like, without violating any NDAs, can you tell us which companies or what kind of companies are pulling, are using your research? Are Boeing or Airbus the main ones that you see interest from, or is it new entrants like ZeroAvia, or it's going to be some startup like in our group here? I know there's quite a few people who are looking at new aircraft platforms. And Jack, I have one more note is I thought
you were going to ask about how do we get the hydrogen to the airport in alternate paths.
I want another line on your chart.
Okay,
Therefore,
we haven't.
I want the fifth.
Okay, let me talk a little bit about that. So from my perspective, over the years, not just us, but many people at NASA, of course, have been interested in using hydrogen in aviation applications. And we've had the good fortune of working with a few, especially at NASA Glenn, and have some publications together with them. Over the years, we also have had Boeing and Airbus interactions, sometimes with Airbus suppliers like Parker Hannifin rather than Airbus. Okay, so these are the big names, right? So big names. Yeah, sometimes we have had nice collaborations with them. At this very moment, we have no active collaborations either with NASA or with Airbus or with Boeing. And from my perspective, Airbus is more committed to it, it seems to me, than Boeing is today. Okay, and I think it's probably just a short-term thing, okay, because of Boeing challenges at this time. The fact that all of these three have for decades already been investing in this, we all know it's part of our future, okay? It is going to be part of our future, okay? The exciting stuff that we've been doing lately is to be interacting with the startups, because I think that is what's really changing everything. And I can't name any names in particular, but we are working with a few. Okay, we're working with a few, and it's not a lot of work that we have with the few. And we don't have a lot of funding to do this work, but I'm so sure that I want this to happen that we're investing even some of our own, discretionary funds in doing things like investing in hydrogen for aviation, and using students on scholarship to do things like this and everything. So it's really we're pulling things together from a set of contributions. Let me just mention one final thing. You saw that the majority of the cost of delivering hydrogen to the airports is associated with the renewable primary energy itself, so the sun and wind power. But if you can get the hydrogen to the airport in an alternative way, and I know that your company, TO2 Verity, did I say that okay?
Verity. Yeah,
okay.
Verity.
Yeah. Is looking at taking renewable ethanol, and which is already delivered to the ports right next door, okay, on trains, pretty efficient, okay. Maybe that can be a primary energy source for the hydrogen. Your presentation at the High Sky event, and so it was pretty cool to see that as another alternative, which we haven't had a chance yet to investigate, but would be pleased to include it in our future analyses.
Yeah, I was surprised to see how large the bar was for the for moving for that part of it in your slides. That surprised me. Thank you very much.
Yeah, thank you.
Thanks. Last question, Sant. I want to get to you before we end.
Yeah, awesome. Thanks, Danielle. Jack, great presentation.
Thank you.
Presentations that got so much data that I've seen. Well, I have got 3 questions and you can choose to answer in the interest of time. So one is the total systems cost. Did you do any trade-off or cost comparison study on the weight, not on the cost, but on the weight between a high temperature fuel cell propulsion system versus a solid oxide fuel cell system in terms of weight? So that's number 1. Number 2 is on the hydrogen tank storage or placement within the airframe, what does FAA's take on carrying the tanks in the back of the vehicle versus the wings of the vehicle? Has there been any regulations or recommendations from FAA on that? Number two. And number three is I was kind of surprised when you showed that the renewable power generation takes much of the cost for hydrogen. I always thought the electrolyzers and the cryogenic storage systems would be the more expensive components. So this is not a really hydrogen problem. This is more of a power production problem upstream with the Department of Energy. So I don't know if you consider nuclear in any of these. I know that a couple of states are looking at nuclear very seriously. But I mean, I'm in this business of, bringing these vehicles to commercialization. I hate to see that it'll be 2050 before there's going to be a reasonable business case for these. And I don't want you to send your PowerPoint to my investors. So I just want to say, what do you think should be done in terms of cost reduction so that we can, if not get to the hydrogen shot, maybe come to a reasonable target commercialization?
Okay, I'm going to try to remember all the questions, and I think I do have time to answer all of them. Maybe not to your liking. We'll have to see. Okay, the first is, have we looked at the comparison of weight associated with high temperature fuel cells and low temperature fuel cells? And absolutely, we have. And we've also looked at high temperature PEM versus traditional low temperature PEM. And this is so there's three different technologies that we're considering here. The first one is proton exchange membrane technology. That's the most popular one. If you look at all those dots on the aircraft that have already been tested with fuel cells, it's almost all proton exchange membrane fuel cells. These operate at basically room temperature up to 60 to 80 Celsius, okay? These are very power dense. Very power dense. That's why we can fit them in cars, and we're already selling them in the Mirais and the Nexos and everything else. And we're putting them into trucks, long haul trucks, okay? But they have a very heavy and high volume heat exchanger requirement for rejecting the heat. If you go to the high temperature PEM, which is operating in the 200 Celsius order of magnitude, maybe it's 160 to 200, okay, 160 to 200. There's a huge advantage with regard to heat rejection, and you have a much smaller balance of plant for that system compared to the low temperature PEM. And so even though you have lower power density of the fuel cell, you might have greater volumetric and gravimetric energy density, okay, with a high temperature PEM, okay? And this is why ZeroAvia is looking at high temperature PEM, okay? So those two technologies we've looked at, and from my perspective, they're very comparable with regard to their weight in the end, okay? The heavier one is the solid oxide, okay? Solid oxide is going to be heavier than any of those, okay? But it also is the most efficient and gives you, and doesn't require all this extra balance of plant. You don't have to do any heat rejection. It operates at very high temperatures. It wants to be cooled by the air that goes through it. And secondly, has this pressurization that happens due to the high temperature. You can't get that from turbochargers, even on high temperature PEM. It's very difficult, but you can with solid oxide. Okay, so these are the trade-offs you have amongst those three different fuel cell types. And again, the most popular kind right now, which is also the most ready for application and has the most investment up to date, is just the low temperature PEM. Okay, that's the one that's kind of ready right now. And that's why Jovi is doing that with that, and others are doing it with that. Second question.
Hydrogen storage, FAA's.
Okay, FAA with hydrogen storage, yeah. Let me suggest that what we have looked at is the center of gravity envelope, and how hydrogen storage tanks, which are heavy, okay, changes that. And as a result, we've had to move things around. You may have noticed in the citation that we put some tanks in front and some in back, okay? But this is primarily because of center of gravity analysis and results for that. When it comes to FAA, we haven't talked to FAA at all, okay, about whether or not they're going to have some requirement that you can't put them, let's say, in the passenger, or maybe you can't put them in the wings for now. Okay, whatever. I don't know what they're going to say about it, but we have been looking at their placement for making sure that center of gravity envelope is honored and that we could, have reasonable control and dynamics of the aircraft in takeoff and landing. Okay, final question.
That's the levelized cost of hydrogen.
Okay, yeah, levelized cost of hydrogen. I think our numbers are realistic. Okay. I trust what we have done in these analyses to show us the reality of what we are dealing with today, and what we expect the future to entail with scientific means of estimating the cost of electrolyzers as they come down, the cost of wind and solar power over time. I trust our numbers. You should know that we have zero, okay, subsidy or program for supporting that hydrogen use, nor any cost of emissions. Okay. There are going to be programs that do this. As a matter of fact, we know that we're going to have the 45V production tax credit, investment tax credits that contribute to these. If you add that to these, you will get all of a sudden in the ballpark of what is cost competitive. Already cost competitive today, if you can get $3 per kilogram, for example. Now, these programs don't last forever, but that's why you also will have to then, if you don't use hydrogen or sustainable aviation fuel, what are you going to be forced to do? You're already being forced to do it when you fly over Europe. You're going to pay a tax for emitting the carbon. If you start to add these to the technoeconomics, they start to look not so bad. As a matter of fact, very attractive as a zero emissions alternative. So yes, my numbers are higher than what the DOE Earthshot says. Our numbers are maybe higher than some others have estimated in the literature, but I think ours are pretty accurate. And with programs that accurately account for the emissions that you would otherwise have, it's worth it. It's worth it.
Thank you, Jack. Appreciate it.
Thank you.
Well, Jack, thank you so much. Always a treat. We'll not keep you any longer, let you get to your class, but please send me those slides. I know a lot of people are going to be eager to look at those. Thanks so much again, and have a fantastic week. I'll see you
You're
everybody
welcome.
next month.
Thank you all.
Bye.
Bye-bye.